Hi guys, how you all doing? Good to see you back on my channel again. The algorithm must have helped, or maybe you're just subscribed to me. So, yeah, reminder: please subscribe to me um, if you haven't yet. Okay, it will be a really big pleasure for me. It will incentivize me to make more interesting videos about calculus and other things. However, today, let's see what we've got for you. Okay, today for you guys, I have a concept called that I don't know if I've created this myself. Maybe this isn't original, but I hope it is. I call it the nested recursive functions. Nested recursive functions. Okay. Let me just. My mum's watching this, by the way. Okay. I'm gonna make my camera. How big should it be? Is this big enough? Is that? Yeah, I think it is. Okay, this is what we have then today. Nested recursive functions. So I have three cases for you. If you guys can think of more, oops, hiccups. If you guys can think of more cases that are interesting, feel free to spam the comments with respectful messages. So let's start with the first one. The first case, e to the x, right? The second is with logs, the third is with the sine function. In fact, if I feel like it, I may make up more as I go, but depends on timing and stuff. So number one, I'm going to define f subscript 1 of x to just be e to the x, okay? F sub 2 of x to be e to the power of e to the x. F3 of x to be e to the x, okay? Quick note with these power towers, by the way. This power tower here can be expressed like this, not like this. E to the x with a bracket this way, right? That's sorry, like this. This is different, right? We are starting from the top and we are going to the bottom. That's how these power towers generally work, okay? And of course, f4 of x is just going to be e to the power of e to the power e to the power e to the power of x. The e power tower is ridiculous. The law goes really, really hard. So if you were interested in coming up with a general form for f sub n of x, where of course n is a positive integer or it's a natural number, whatever you want to call it, then I think you could use the tetration notation to express this. I would do it like this: e tetrated to the degree of n plus 1, and then all of that raised to the power of x over e. The reason I would... Oops, I dropped my pen lid. Oh no, it's a disaster. The reason I would express it like this is because, well, first up, what does this bit even mean? I thought exponents were meant to go to the right of the base, not to the left, right? Well, to the left, for example, let's say you have e tetrated the second degree. This just means e to the e, right? E tetrated 3 times is just e to the e, okay? First up, that's just notation. Ignore that. In this case, e tetrated n plus 1 times is just e to the power of e to the power of e to the power of e, da 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 da, and there's n plus 1 many e's, right? And then put all of that, I'm trying not to make this look like a matrix, put all of that to the power of x over e, you get that one of the e's cancels out and you're left with x going in there, right? Which gives you e to the dot 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 n many e's to the power of x, right? And that's how I'm defining f sub n of x to be, okay? That's not really relevant for this video. It's just an interesting little side thingy topic that I thought up. Give me a sec, my software is glitching again. Please subscribe so that I can get enough money to buy more software. Sorry about that, I think it works now. Okay, there we are. Full screen. Yep. Sorry for the, yeah. So fn of x I defined as this sort of tetrated thingy to the power of x, right? that's not relevant for this video, but tetrations are an interesting concept. Basically, repeated exponentiation. But yeah, the question that I have for today, not just these functions, if you wanted to actually define it recursively, it would be fn plus 1 of x is just equal to e to the fn of x, right? Just as a side note. But anyway, I'm interested in the gradients. I forgot to mention this earlier. The gradient function of these nested recursive functions, okay? So the question is, do we notice a pattern as we increase the n value for the resulting gradient functions or the derivatives? So let's start from f1 of x, okay? So what do we have? f1 of x equals to e to the x. What's the derivative of f1 of x? Well, the derivative of that is of e to the x, which is just e to the x, right? This is like the only function out there that differentiates to itself, apart from f of x equals 0. Of course, that also differentiates to itself. But yeah, the e to the x function differentiates to itself. Okay, nothing special there. How about the derivative of f2 of x? Well, what do we have? Well, here we're going to have to use the chain rule. The chain rule in this situation is basically used like this. The derivative of e to the power of some function of x, let's call it h of x. This is equal to e to the h of x multiplied by h prime of x, right? So let's use this chain rule to differentiate e to the x. In this case, instead of having h to the x, we have e to the x here, right? So let me actually try and color coordinate this. Let's see. e to the x. Okay. Yep, this is good enough. So first we have e to the h of x. In this case, h of x is e to the x. It's equal to e to the h of x, which is e to the x, multiplied by the derivative of h of x. In this case, h of x is e to the x. The derivative of that is e to the x. That is the derivative of f2 of x. Let's work on f3 of x prime, of course. This is equal to the derivative of e to the x. Okay? And first of all, chain rule once again. So we repeat the same exact function, e to the x, multiplied by the derivative with respect to x of the exponent e to the x, right? And luckily for us, we already know that the derivative of this is over here, which is e to the x times e to the x. So we end up with e to the x times what we've already worked out, which is this, okay? Okay, it's quite dense, I know. This is a lot of stuff to take in. Let's do one more iteration of this, and then we can generalize it. We can assume that this pattern goes on for all like integer values of n, I suppose. So the derivative of, we have 4e's to the power of x. This is equal to, we repeat the same function again, and then we multiply it by the derivative of what was at the exponent, which is this thing here, e to the x, right? Luckily for us, we already know the derivative of this because we've already done that. That's just the derivative of f3, okay? So we end up with all this stuff times what we got over here, right? Of e to the x times e to the x times e to the x, right? And now let us go all the way back and sort of express all of the gradient functions in terms of fn of x, right? So in this case, the derivative of f1 of x is just e to the x, which is also f1 of x, right? The derivative of f2 of x is equal to, well, that's f2 of x, and this is f1 of x, okay? So we have f2 of x times f1 of x. Okay, I hope that's self-explanatory. The derivative of the third iteration is, well, here we have a power tower with 3 e's, so that's f3. Then we have the same power tower with 2 e's and then with 1 e, right? Whoops. f2 of x, f1 of x. If we do the same thing for the fourth iteration, we get f4 of x times f3 of x times f2 of x times f1 of x. Okay? So we can just generalize this for all integer and for all natural n values. Therefore, we can say that the derivative of fn of x is equal to fn of x multiplied by fn minus 1 of x multiplied by fn minus 2 of x all the way down to when we reach f1 of x, right? This is basically like, it's not a factorial, but it feels like a factorial, right? Because we're just starting off with n and we're multiplying with all of the values like one less than it, right? One less and one less and one less. It's really, really interesting. And luckily for us, there is a closed form notation for this kind of product. We call this the pi notation. Essentially, have you heard of the sigma notation before? That's this, right? The sigma notation, that's just summation, okay? So essentially, let's say you have sigma, or the sum, as k goes from 0 to 5 or something, of some arbitrary function of k. Let's call it g of k. This is just equal to g of 0 plus g of 1 plus g of 2 all the way to g of 5, right? If we replace the sigma with pi, however, we have the same exact thing, just with a pi instead of a sigma. That's equal to g of 0 multiplied by g of 1 multiplied by g of 2 all the way to g of 5, right? In other words, if you want to explain it like to someone in English, sigma, that's like the Greek letter for S, right? And S is for sum. Pi is the Greek letter for P, and P is for product, right? Or multiplication, so we're multiplying, right? Essentially, sigma is for discrete summation, and pi is for discrete multiplication, okay? I think I can rub this out now, right? Safely rub this out. Yep. And if we wanted to express our sort of gradient recursive function thingy in the pi notation, well, we would have this. We would have the product of, let's say, f k of x as k goes from 1 to n, right? This is another way of writing. This is also the same as f1 of x times f2 of x times f3 all the way to fn, okay, of x. I'm just not going to write the x's. I'm not interested. But yeah, that's our first gradient function, I guess, generalization done, right? The derivative of e to the however many e's to the power of x you have is equal to this thing over here, right? It's equal to e to the x multiplied by e to the x multiplied by e to the x multiplied by however many e's you had in your original function. Really, really interesting stuff, I know. Okay, so yeah, that's our first one. Our first function done, our exponential function. That's a lot of work, I know. The second function I want to work with is logs, ln, or natural log, or whatever you want to call it. Whoa, it's raining like crazy right now. Whoa. I'm impressed, to be honest, at the rain right now. Of course, we're in England, so you shouldn't be surprised when it randomly rains heavily like this. But yeah. Our second function, I'm going to define f1 of x to be the natural logarithm of x, okay? For those of you who are not fluent with logarithms, or you don't know what logarithms are, or there's many excuses you could have, I forgive you. The logarithm is the inverse of exponentiation, right? So you know how f inverse of f of x is equal to x, right? That's just how functions work. Well, in this case, if f inverse of x is equal to e to the x, then f of x is natural logarithm of x, right? But yeah, natural log. Another way to write natural log is logarithm base e of x, right? The way logs work is if you have log base e of x equals y, this is the same as saying that x equals to e to the y, right? That's just how logarithms work. That's the definition of the logarithm, right? That's for those of you who maybe you haven't learned logarithms yet for some reason. I didn't know what the logarithm was until I reached year 12, I think. So if you don't know what they are, you probably have an excuse. Anyway, I've defined f1 of x to be the natural log of x. I've defined f2 to be the natural log of the natural log of x. And f3 to be, well, it's pretty self-explanatory, right? I'm just going to write one more iteration of this. ln, 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 ln x. Too many brackets. Cool, right? That's what I'm defining the function to be. If you want to define it recursively, that's fine. You can write fn plus 1 of x equals to the natural log of fn of x, right? Oh well, that's the natural log for you, I suppose, right? Is there a general way to write this? Well, have you ever seen this notation before? It really bugs me out, but I think it's correct. So basically, f to the 2 of x is the same as f of x, right? I know this is awkward because this doesn't apply to like trigonometric functions. Like if you write sine squared of x, this isn't the same as writing sine of x, right? In reality, sine squared of x is just sine of x times sine of x, right? So yeah, I think sine of x is like a weird exception to all trig functions are a weird exception to this notation. But I think generally this is an acceptable notation to use that mathematicians may use. However, it is very confusing, so we would rather write f of x as opposed to f squared of x, right? But yeah, I'm not going to confuse you today. I've done so enough in my previous video. Let's get on to differentiating all of these behemoths and see what we can do. Okay, I'll start with the first function then, the derivative of f1 of x, or of ln, or natural log of x. Let's do it over here. So f1 of x prime, or the derivative of f1 with respect to x, equals to the derivative of the natural log of x, which is just, you already know that's 1 over x, right? In other words, the integral of 1 over x is natural log of x. That's another way to think about it if you're more fluent with integrals, which is really weird, really. I think I'm the only one in this room who is better at integrating than differentiating, but that's just me. Okay, what do we have then? f2 prime of x is equal to the derivative of the natural log of x, right? And for this, we're going to have to use the chain rule again, okay? And the chain rule for logarithm differentiation works like this. If you have the derivative with respect to x of the natural log of some arbitrary function of x, I'll just put it in blue, any function of x, natural log of that function, that can be written as f prime of x over f of x, right? The derivative of the argument divided by the argument itself. That's how you differentiate the natural log of some arbitrary function f, right? In this case, instead of having f of x, we have natural log of x, right? So the derivative of ln of x is equal to the derivative of the inside. Let me just put it in blue. The derivative of the inside divided by whatever was on the inside. And we already know that the derivative of natural log is just 1 over x from earlier, okay, from the previous line, over ln of x. And this can be written as 1 over x ln of x. That's just self-explanatory, okay? Let's try this out for f3 of x, and then for f4 of x, then we can generalize some stuff. So f3 of x differentiated with respect to x is equal to the derivative with respect to x of ln of this, natural log x, right? This is equal to the derivative of the blue part or the argument of the log, shall I say, divided by the argument itself, right? And luckily for us, we already know the derivative of ln of x. That is already worked out here to be 1 over x ln x, right? So all in all, we end up with 1 over x natural log x times natural log of x, right? That is f3 prime of x. Let's do f4 prime of x now and see what happens. f4 prime of x equals d over dx ln x. Let's do that in blue as well, the inside. 1, 2, 3 logs inside the fourth outer log of x, right? Equals to the derivative of the blue bit. The derivative of what? ln x, right? Divided by, once again, the stuff like that, the argument of the outside log, right? And we already know the derivative of ln x. That is just over here, right? The previous line already told us that. So if we clean everything up, we get x, natural log x, natural log x, multiplied by the blue bit, which was natural log x, right? Now let's go back to the start, and let me just introduce you one more thing. I'm going to define f naught of x to just be x on its own. No natural log, just x. Okay? In other words, ln of e to the x, but whatever. Let's call it x. Okay? Of course, f minus 1 of x I'm going to define to be e to the x. Oh, wait. We have a crossover between the first and the second functions. No way. Essentially, what I'm trying to say is, well, in order to get from f4 of x to f3 of x, you exponentiate f4 of x, right? In order to get from f3 to f2, you exponentiate f3. And then you exponentiate f2 to get to f1. To exponentiate, in order to get to f0, you exponentiate f1. And then if you exponentiate f0, you can get something, what I would call f, there's not enough space on this OneNote page. I'll just write it down here. f negative 1 of x equals to e to the x. And that leaves us with that. That is so cool, right? We have an unexpected meetup between the exponentiation, the exponential function and the log function, right? But yeah, maybe that's for some other time. I feel like narrating a Teenage Mutant Ninja Turtle storyline right now with all of the interweaving plots. Pretty cool show, check it out. Anyway, we have to define all of these derivatives in terms of f subscript whatever of x, right? 1 over x, that's just 1 over f naught of x, right? Okay, 1 over x log x is just 1 over f naught of x times f1 of x. I'm not even going to write the x's at this point, I'll just write f. The derivative of the third function is 1 over f naught, which is x, times f1, which is natural log of x, times f2, which is natural log x. If you do the same thing for the fourth iteration, you get 1 over f naught times f1 times f2 times f3, right? So therefore, we can conclude that the derivative of fn of x in this case is equal to 1 over f0 times f1 times f2 all the way to fn minus 1, right? The reason n minus 1 is because here we have a 4, f4 of x prime, and we end up with a 3, not a 4, right? So that's why we have the n minus 1 subscript. So therefore, if we wanted to use pi notation, you get 1 over pi as k goes from 0 to n minus 1 of fk of x, right? So that's the derivative of the recursive nested logarithm function, as I would like to call it, as I would propose it to be called anyway, right? Pretty cool in my opinion anyway. Yes. Okay, now the third thing that we have to discuss. Okay. All right, the third thing is the sine function that we're going to do. So let's see. I'm going to define f1 of x to just be sine of x. f2 to be sine of x. f3 to be sine of x, right? Let's write it like this. And f4 to be sine of x, right? Cool. So, in other words, fn plus 1 of x is just fn of, or sine of fn of x, sorry. This feels like an iteration as well. It is, but, you know, okay. So, now we have to do the derivative and see what we get, okay? Yeah. Let's start with f1 of x. The derivative of f1 with respect to x, we're not talking about the formula 1, we're just, I'll stop. The derivative of sine of x is just cosine, obviously, right? If you didn't know this, you may want to recap your differentiation by first principles, your sign addition rule, your squeeze theorem, your all of that, okay? You may want to recap those, there's plenty of stuff on YouTube. Okay, f2 prime of x is the derivative with respect to x of sine of x, which is what? All right, let's see. So we're going to use the chain rule again. And for the sine function, the derivative of sine of some arbitrary function is equal to what? Well, it's equal to the derivative of the sine, which is cosine, right? Multiplied by the derivative of the inner function. Okay, that's the chain rule for the sine function. I guess it would work in a similar way to the log function as well, the chain rule, because ln f of x. Because, well, first of all, you get 1 over, well, the derivative of ln x is 1 over x, right? So the derivative of ln f of x should be 1 over f of x, right? However, you have to multiply by the chain, which is f prime, right? So yeah, it's the exact same concept just with sine. And the exponential function as well, d over dx, e to the f of x. The derivative of e to the f of x should be e to the f of x, but you multiply by the derivative of the argument of the function, right? Essentially, you have an outer function with an inner function inside. Differentiate it, you get the derivative of the outer function with the inner function inside of it, multiplied by the derivative of the inner function. That's the chain rule for you, okay? So the derivative of sine of x is just going to be, I'm going to write the inner sine of x in blue again, as I usually do. Well, you get cosine of sine of x multiplied by the derivative of the blue part, which is the derivative of sine, which is cosine. Okay? How about f3 prime of x? That's just d over dx of sine of x. Right? And the derivative of that is, well, you get first of all cosine of the same exact argument multiplied by the derivative of the inside, d over dx sine of x. Luckily, we already know what d over dx sine of x is. That's just cosine of sine times cosine. So you get cosine of sine of x multiplied by cosine of sine of x multiplied by cosine of just x. No sine, just x, right? So that's a derivative of the third iteration of the function. Let's do the fourth iteration now. f4 prime is equal to d over dx sine of x. sine x, which equals to cosine of the inside, sine x, multiplied by the derivative of the inside, or sine x, which is equal to cosine of sine of x, can't be bothered to write it properly, times d over dx of sine of x, which we already know to be this monstrosity here. So we get cosine of sine of x times cosine of sine of x times just cosine of x, right? Yeah, I think now we are ready to generalize it and assume that this pattern goes on forever for all positive integer values of n, right? One more trick that I'll do, I'm going to define f naught of x to just be x, right? Because you just, once again, in order to get from f4 to f3, you apply sine inverse. To get from f3 to f2, sine inverse, sine inverse. Eventually, to get from f1 to f0, you apply sine inverse to the sine of x to get back to x, right? So, let me just move this chain rule stuff up. Okay. Yes. So the derivative of f1 of x is just equal to cosine of f0 of x. I'm not going to write the x's. The derivative of f2 is equal to cosine of f1 times cosine of f0, right? The sine of x is f1, and the x is f0, okay? The derivative of the third function is equal to this thing over here, which is equal to cosine of the two sines, which is cosine of f2, times cosine of one sine, which is cosine of f1, times cosine of f0, right? And for the fourth iteration, you get cosine of f3 times cosine of f2 times cosine of f1 times cosine of f0, right? And so therefore, the derivative of fn of x is just equal to cosine of f0 multiplied by cosine of f1 multiplied by cosine of f2 until you get to cosine of, is it fn or fn minus 1? We'll have to check. Well, the fourth iteration over here yielded you f3, so fn minus 1, right? So therefore, we can write that the derivative of fn of x, in our case, is equal to the product of cosine of fk of x, as k starts from 0 and ends at n minus 1. Okay? If you wanted to, you could also do a shift of index if you wanted to. Like, if you wanted to, let's say, I don't know, instead of starting from 0 and ending at n minus 1, if you wanted to start somewhere else, you could probably do that as well, but I'm not interested. But yeah, that's our sine function then, all right? So we get that fn prime equals the product from 0 to n minus 1 of cosine of fk. This is, I guess, pretty similar to the logarithm, right? Yeah, really similar to the logarithm. The only difference is the logarithm, we get 1 over product of fk, right? With the sine, we get cosine of fk, right? So in fact, we could generalize this to any function that we want, I suppose, right? And with the exponentiation one, I guess, okay, this pattern doesn't really hold for it, but what I'm proposing to you is that if you have if you define fn plus 1 of x to just be f of fn of x, right? Any f, where f is like cosine, f could be sine, f could be ln, f could be anything. I'm proposing that the derivative of fn of x is equal to what? The product, as k goes from 0 to n minus 1, of f1 prime of fk of x. That's what I'm proposing. I don't think this works for everything. It clearly doesn't seem to work for the exponentiation function here, e to the x. Don't think it works for that. But then again, who knows, right? It could. But yeah, really, really cool discoveries here. I'm going to do one more, then I may... Okay, let's see. How am I doing with the timing? Geez, 35. 35 minutes. Should I try this out with... I'm trying to think of a function to experiment with. Another one, right? Let's do it with tan. Why not? So number 4, tan of x. Right? The reason I picked tan is because despite the fact that it's literally raining right now, it is like technically we are into the summertime, right? It's nearly June. We are pretty much in summer. And I'm expecting myself to get a tan. That's why. So let's define f1 of x to be tan x and f2 to be tan of x. Okay, so far so good. f3 to be tan of x and f4 to be tan of x. This actually looks ugly, but we try our best. And fn plus 1 to be tan of fn, right? In other words, fn plus 1 can be written as f1 of fn. Yeah, f1 of fn. Okay. Now let's see. So the derivative of tan. Let's start off. f1 prime equals the derivative of tan, which is equal to secant squared of x, right? First up, why is the derivative of tan equal to secant squared? Like, how on earth are you meant to remember that in an exam or something? That's a genuine problem that my friends keep bringing up with me. How on earth do I remember it? I'll show you a simple trick. So you already know that the derivative of sine is cosine. And you already know that the derivative of cosine is negative sine. If you're not sure about that, go back to your notes, check your first principles, check your squeeze theorem, check your addition formula stuff, right? You should be really familiar with these by now, especially if you're in like Calc 2 or Year 13 or whatever, right? All right, so the derivative of tan of x can be written, well, tan is just sine over cosine. That is literally the definition of tan of x, right? And there's something called the quotient rule. The quotient rule goes like this. If you have a derivative of two functions that are divided by each other, this is equal to vu prime minus uv prime over v squared, or v times v, right? That is the quotient rule. This is basically the chain rule, or sorry, this is basically the product rule, but instead of having uv, you have uv to the negative 1, or u over v. That just gives you the quotient rule, right? But yeah, here the derivative of sine over cosine. In this case, let me try and color coordinate everything. Instead of u of x, we have sine of x, right? So I'm going to do it like this, sine of x. And instead of v, we have cosine of x, right? Which I'll do in purple. That's looking fine. Okay. Let's see. Yeah, there. Okay. So first we have vu prime, or v is just cosine. U prime is a derivative of sine. Right, I'll put a prime like this. Minus uv prime. U is sine, and v prime is cosine prime. Over v squared, or cosine x squared. Right? So this equals to, well, cosine of x times the derivative of sine is just cosine. And then you have sine x times the derivative of cosine, which is negative sine, over cosine squared of x. So on the numerator, you get cosine squared of x plus, okay, let me just fix up my handwriting, plus sine squared of x. The reason you have a plus is because the two negatives here and here multiply to make the plus, right? Over cosine squared of x. And the numerator is just equal to 1. That is what we call the Pythagorean trig identity. How could you prove that? Well, all you need really is a unit circle, right? You know x squared plus y squared equals r squared, right? Pick, yeah. Let's let r equal 1, so we have a unit circle. Let's pick a point on this unit circle, and let's call it xy, right? Of course, the radius of the circle is 1, so the length going from the origin to that point is 1. We can create a right-angled triangle like so, where the hypotenuse is 1, and then let's label this angle theta. The side opposite to theta is x, and the side adjacent to theta is y. If you use your SOH, TOA, or whatever other goofy acronyms you can think of, you can derive from this that x is equal to cosine of theta and y equals sine of theta, right? Because, x over 1, y over 1. X over 1 is opposite over hypotenuse. Y over 1 is adjacent over hypotenuse. I got this the wrong way around, didn't I? Sorry. Yeah. No, yeah, I did. So x is the adjacent and y is the opposite, sorry. So x is cosine and y is sine. Sorry, that's not my word. But yeah, the 1 doesn't even need to be written. So you get x is cosine and y is sine, right? And you know how x squared plus y squared equals 1, right? This implies that cosine squared plus sine squared is also equal to 1, right? That's how you can prove the Pythagorean trig identity. You use Pythagoras formula, use whatever, right? But yeah, that's how cosine squared plus sine squared is 1. You're left with 1 over cosine squared, which is equal to 1 over cosine x squared, which is equal to secant x squared, right? That's the definition of secant is just 1 over cosine, which is equal to secant squared of x. You can use this notation here. That is how you derive the differentiation of tan of x, using the derivative of sine and cosine and by using the quotient rule, okay? So now let's use the chain rule for tan of x. I said that the derivative of, let's say we have a function, a. Okay, no, that's not a function. Let's call a function, let's call it like z of x, right? Instead of z of x, we have z of another function of x, right? The derivative of z of y of x, where z and y are functions of x. I'm not going to bother with the handwriting. Where z and y are functions of x, the derivative of z of y of x, I said, is z prime of y of x multiplied by y prime of x. That is the chain rule, okay? How do you arrive at this? You can just take a substitution. Let u equal y of x. Let me do that right now, actually. Let u... Where's my pen not working? My pen ran out of battery. How thrilling. Okay. Once again, reminder, please subscribe to my channel. It's going to be really nice. Let me just do this. Okay. All right. Yeah. Okay. Yeah, my pen is just charging and stuff. Once it reaches 10, I'm just going to unplug it because we don't really need much battery. All right. As you can tell today, I am utterly dripped out. I've got the navy blazer jacket with, I've got this like, I don't know what this is. It's like a jumper shirt, polo shirt hybrid thingy. But it's really, really nice. And I've got the pocket square, right? No necktie today because the weather is a little bit hot, but yeah. Okay. Let's see. All right. Let's get back to this then. I was doing the chain rule. Let u equals to y of x. Oh, my pen isn't working again. No. Okay, now I have to actually pause and restart. I think I'm ready now. Sorry about the delays and stuff. Let's get going. So let u equal to y of x. Let's differentiate both sides. Du over dy equals to y prime of x. Okay? That means, let's see. D over dx, z of u is equal to what? Z prime of u multiplied by du over dx, right? Wait, this is just pointless. I'm just repeating. Okay. Yeah, that's one way you could go about it. But then the issue with it is I just realized I used circular reasoning. But let's just assume this for another video, okay? But this initial statement I said was definitely true. Of the derivative of z of y is equal to z prime of y times y prime. Okay? If we use that sort of rule to differentiate tan of some arbitrary function, you get the derivative of tan is secant squared of the arbitrary function multiplied by the derivative of said function, of the inner function, that is, right? F prime of x. So now using that, what do we have? The derivative of the first function is secant squared. The derivative of the second function is d over dx, tan of x, which can be written as secant squared of the inside multiplied by the derivative of the inside, which is secant squared of x. If you do the same thing for the third, tan of x, you get what? Secant squared of tan of x multiplied by the derivative of tan of x, which we already know to be secant squared of tan times secant squared of x, right? And so, yeah, therefore it's clear that the derivative of fn of x is just equal to the product of fk as k goes from, well, not k, sorry, of secant squared of fk as k goes from 0 to n minus 1, right? Same thing applies there. Or in other words, let's see. Yeah, the reason why k starts from 0 is because we have secant squared of x here, this x. f0 equals to x, right? But yeah, therefore I think it holds true for this function as well, that the derivative of that equals to this, where we have f1 prime of fk, like this, right? It's really, really weird and awkward stuff, but I really enjoy this kind of thing, okay? That's with tan. All right. Does the same thing work with E? I think it does, you know. I'm not really too sure, but okay. I mean, I guess technically it does because instead of you can like re-index this, I swear, right? Instead of k going from 1 to n, you can let like k equal to u minus 1 or something, right? Which means if k goes from 1 to n, then that means that u goes from, let's see, if you let k equal to 1, you get u is equal, okay, no, u plus 1, sorry, u plus 1. If k is 1, then u will be 0, and if k is n, u will be n minus 1, right? So our pi notation can be written like this. Pi, instead of k going from 1 to n, we have u going from 0 to n minus 1. And instead of fk, we have f of n minus 1, right? Not u minus 1, sorry. However, this isn't quite the same, I guess, as this, right? k going from 0 to n minus 1 of f1 prime of fk, right? Because we have a f u minus 1. I can rewrite this. Instead of u, we can use k. These are just dummy variables. Remember my previous video of fk minus 1 of x, right? I'm trying to... Yeah, there surely is a way. But I'm pretty sure, though, that you could use this theorem here that I've made. In fact, let's try it out directly. Let's let let's see. Let's let f1 of x equal e to the x, and fn of x equals whatever we said it was earlier. E tetra to the n plus 1 to the power of x over e. Okay. Right. So if we use this, fn prime, we get the pi as k goes from 0 to n minus 1 of f1 prime of fk. f1 prime, by the way, is e to the x, right? But instead of e to the x, we're inserting e to the fk, right? So we get pi, k goes from 0 to n minus 1 of e to the fk, right? Which is equal to e to the f0, which is e to the x, times e to the f1, which is e to the power of e to the x, times e to the f2, which is e to the... times all the way to... you get n minus 1 lots of x's, I think. I think it works just about, but it's really, really awkward. Maybe there's a mistake I made somewhere. But yeah, exponential, I think it definitely works. So yeah, therefore I can confidently say that the derivative of, let's say d over dx, f to the power of n of x. This notation basically means f of f of f of f of x, right? Where we have n lots of f, right? This is equal to what we said it was earlier. Product k goes from 0 to n minus 1. Product k goes from 0 to n minus 1 of f prime of fk. F prime of fk. So yeah, we have derived this new rule that I've made for you guys. What should I call it? Please suggest me in the comment section what I could name this silly looking rule, because I think it's pretty fun, right? Yeah, in fact, just to be sure, yeah. Oh well, without further ado, thanks for watching. Have a nice day, guys. I really appreciate your presence over here on this channel, and without further ado, good luck on your studies, job, whatever it is that you guys want to do. Thanks for watching. Like, subscribe. Please give me feedback in the comments, and have a good one. Thank you.